Welcome back to AI Paper Podcasts. Today we're digging into a really interesting paper. From memorization to reasoning in the spectrum of loss curvature. It offers a pretty fresh perspective on how transformers manage knowledge.
Yeah, it's a fascinating one. So for the quick summary up front, the paper essentially maps out where memorization and generalization live inside model weights using loss curvature. Think of it like the shape of the air surface. They use KFAC to approximate this.
And the big surprise, the thing that really jumps out, is that when you look across the whole data set, all that verbatim memorization, the brittle stuff like facts and simple math, it's actually found in the low curvature spots, the flat valleys, not the sharp peaks.
Exactly, which is kind of the opposite of what some previous work suggested looking at single points.
Yeah.
Here, the general rules, the stuff that lets the model generalize, that lives in the higher curvature, the sharper directions.
And this led them straight to a new way to edit weights KFE truncation. They showed it removes memorized stuff, even stuff the model memorized but wasn't told to forget, way better than, say, balanced subnet.
Right, and with less damage to the model's overall coherence, lower perplexity. Plus, this whole analysis lets you place different skills on a spectrum. Logical reasoning, super robust, high curvature, but closed book question answering, arithmetic, much more fragile, relies on those low curvature bits.
Okay, let's unpack that curvature idea because, like you said, it feels a bit backwards. We all know these models can just spit back training data, which is a huge problem for copyright privacy.
And we also want them to generalize, to actually understand that the question is, how are these two things represented inside? Where's the switch?
So the old idea was a specific memorized fact creates a sharp, deep, narrow valley in the loss landscape for that specific data point. High curvature makes it brittle, right? A small nudge and it's gone.
That was the intuition for individual points, yeah. You might think lots of memories mean lots of sharp valleys.
But this paper says, hang on, zoom out. Look at the average landscape across all the data.
Precisely. Think about the general stuff, first grammar, common sense reasoning, how objects usually look. These are used by almost all the data points. So when you average the curvature influence across the whole data set, these general mechanisms show up consistently. They maintain this sort of moderate to high curvature. They're the shared foundation.
Okay, that makes sense for the general stuff. But what about the thousands of specific, unique things it memorized, like exact quotes or specific addresses?
Right, those are idiosyncratic. A specific quote only applies to that training example. So the weight adjustments needed for that quote point in a very specific direction, but the adjustments for a different quote point somewhere else entirely.
So when you average across the whole data set,
they kind of wash out. They cancel each other out in the aggregate picture. The specific tweaks needed for massive amounts of verbatim recall don't contribute much to the shared curvature signal. And the result is, counterintuitively, that the bulk of this specialized, memorized information ends up residing in the directions that are, on average, much flatter, low curvature.
So high curvature equals shared, robust structure. Low curvature equals the pileup of specific, often brittle, memorized details. Okay, how do they actually measure this average curvature without computing something impossibly huge?
That's where KFC comes in, Kronecker factored approximate curvature. It's a clever way to approximate the Fisher Information Matrix, the FAM. The FAM basically is that dataset average measure of curvature we want, but it's enormous for big models. KFANG uses some matrix tricks to make it feasible.
Can you give us a non-math analogy? What's KFAG doing?
Okay, imagine you're trying to understand the acoustics of a big, complex room by listening to the overall sound. KFAC is like a sophisticated analysis tool. The high curvature components it finds are the loud, dominant frequencies, the consistent sounds that define the room's main echo or resonance. That's your general structure. The low curvature components are like the accumulated background noise, all the little scattered whispers, individual coughs, faint echoes that don't sync up. They're there, they contribute to the overall sound level, but they aren't part of the main shared acoustic signature. KFC lets you decompose the model's weights into these components, these eigenvectors, ordered from the loudest, most shared signal down to the quietest, most idiosyncratic noise.
Got it. A sorted list from core structure down to specific noise. So did the experiments actually show that this noise correlates with memorized stuff?
They absolutely did. They ran a key experiment measuring how strongly these different KFAC components, these eigenvectors, activated when the model processed memorized data versus clean, non-memorized data.
And this worked better than just, say, doing a standard SVD on the weights.
Much better. SVD didn't give nearly as clear or reliably sorted a separation. KFA surely pinpointed the difference.
Okay, let's get concrete. What were the numbers for the language model? Olmo 7B.
Right, so looking at one specific layer, layer 22's MLP input, the split was really clear. The bottom 50% of the eigenvectors, the ones K-C identified as lowest curvature, our noise, these activated 23.1% more strongly on memorized data compared to clean data.
Wow. Okay, so the stuff flagged as low curvature really lit up for memorized inputs. What about the other end, the high curvature bits?
The top 10% of eigenvectors, the supposed core structure, they activated 26% more strongly on the clean general data compared to the memorized data. You see this nice gradient activation on clean data drops consistently as you go down the curvature spectrum towards the memorized end.
That's pretty compelling evidence for the mapping. And this wasn't just an LM thing.
Nope, they found the same pattern in Vision Transformers' VIT-based models, especially when they train them with some deliberately noisy labels, which forces more memorization. In the VIT, the top 10% eigenvectors activated more than twice as strongly on clean data versus memorized data in the final layer. It seems to be a general principle.
Fascinating. And they linked this to weight decay, too.
Yeah, they found that training VITs with higher weight decay, a standard technique to improve generalization by penalizing large weights, actually made this separation in the curvature spectrum even more pronounced. It pushed the model to rely more on the high curvature general components and less on the low curvature specifics.
Okay, so the map seems solid. High curvature, general, robust. Low curvature, specific, memorized, brittle. This naturally leads to the editing procedure, right? The KFA truncation.
Exactly. It's elegant because it flows directly from the finding. If generalization lives in high curvature and memorization in low, just keep the high and ditch the low.
How does it work in practice?
They calculate the KFAC eigenvectors and their associated curvature values. Then they decide on the threshold, like keeping the top components that account for, say, 90% or 99% of the total curvature mass. Everything below that threshold, the low curvature eigenvectors, they just zero out their contribution to the weight matrices.
And crucially, it's unsupervised, right? It doesn't need a list of things to forget.
Correct. No forget set needed, which is a huge practical advantage over supervised unlearning methods like Balanced Subnet, BSN, which needs examples of what you want removed. KFA just targets the structural correlates of memorization.
So how did this unsupervised structure-based surgery compare to the supervised BSN?
The results were pretty striking, especially on Almost 7B. First off, KFC resulted in a model with lower perplexity, 22.84, compared to BSN's 23.59. That means the model edited with KFC was sort of generally more coherent, less damaged by the forgetting process.
Lower perplexity is good, but the real test is forgetting stuff it wasn't explicitly told to forget, right? The generalization of unlearning.
That's the killer result. They used this external data set of historical quotes that the model had clearly memorized during training, but which wasn't part of any supervised unlearning step for BSN. BSN still recalled these quotes with 60% strict accuracy. It didn't generalize the forgetting well. KFA slashed the recall on those unseen quotes down to just 16.1% accuracy. It wasn't just forgetting specific examples, it was removing the capacity for that kind of brittle verbatim recall much more broadly.
That is seriously impressive for an unsupervised method. What about the vision models? You mentioned VITs earlier.
Yeah, the VIT results are almost weirdly good. Applying KFA truncation dropped the memorization accuracy on the noisy labels from about 81% down to just 3.5%. Huge drop.
Okay, expected. But what else?
Get this. The accuracy on predicting the original, ground truth labels for those noisy images actually increased significantly, up to 66.5%. And even better, the model's overall validation accuracy on clean, unseen images improved from 67% to almost 72%.
Wait, hold on. You remove components associated with memorization, and the model gets better at its main generalization task. How does that work?
It strongly suggests those low curvature components weren't just storing noisy labels. They were likely implementing brittle, overfitted strategies that actually hurt performance on the general validation set. Removing them acted like a really effective, targeted form of regularization. You're cutting out the harmful static, letting the core signal shine through.
So it's not just deletion, it's like model refinement.
Yeah.
Pruning away the parts that hinder generalization. And you mentioned robustness earlier.
Yeah, both KFA and BSN showed better robustness to certain kinds of stress tests, like perturbing input positions compared to older unlearning techniques. The stability seems linked to preserving that high curvature core.
Okay, so this KFA truncation isn't just for forgetting, it's a probe. By seeing what breaks and what survives when you cut out the low curvature stuff, they could map different abilities onto this spectrum. This moves us beyond just memorization versus generalization.
Exactly. This is where it gets really insightful for understanding what these models can actually do. They benchmarked a range of tasks after applying the KSC edit.
What stayed strong? What relied on that high curvature, robust core?
Logical reasoning tasks showed incredible resilience. Things like solving Boolean expressions or tracking objects in simple narratives. They retained between 95% and even up to 106% of their original accuracy.
Wait, over 100%. Performance improved sometimes.
Yeah, particularly on Boolean expressions, sometimes they saw a small boost, like up to 6%. Again, it suggests that removing the low curvature clutter, maybe distracting memorized patterns, actually lets the core reasoning mechanisms operate more clonely.
Fascinating. Okay, so reasoning is robust. What was fragile? What depended on those low curvature components they removed?
Two main areas stood out. Closed book fact retrieval, just asking the model for facts it has to recall internally, that was definitely sensitive. Retention dropped to somewhere between 74% and 86%, still somewhat functional but clearly impacted.
And the other area?
Arithmetic. Basic math calculations turned out to be the most brittle capability they tested. Accuracy there plummeted significantly, retaining only 66% to 74% of the baseline performance.
Wow. So precise calculation lives in the fragile zone. Did they see why? Like in the activations?
They did. When they looked at the hidden states of the model while it was doing simple math problems, the activation patterns looked a lot like the patterns seen for purely memorized sequences. They skewed heavily towards activating those bottom low curvature components.
So the model isn't implementing math as a general, robust algorithm in the high curvature space. It's more like memorizing calculation pathways or results in the low curvature, brittle space.
That's what it strongly suggests. It seems like precise calculation, at least in these models, is treated more like a specialized, memorized skill than a fundamental, generalizable reasoning process.
That has huge implications.
Yeah.
And even within fact retrieval, it wasn't all equally brittle, right?
Correct. They looked at a data set of factual relations and found a clear link to frequency. Super common facts, like the largest city in a country largest city, were mostly fine after the edit. High curvature knowledge, presumably. But rare facts, like the CEO of a specific company CEO, those were decimated. Accuracy dropped by like 78% compared to baseline. Low curvature seems to hold the rare specific stuff.
And they had that great GSM-8K math example that really illustrates the point.
No, yeah, that was perfect. The model was asked a multi-step arithmetic word problem. The edited model, post-KFE truncation, generated the exact same chain of thought. It identified all the right steps, the logic was perfect, high curvature reasoning intact. But the very last step, the final calculation, it messed up. It calculated 20 plus 80 plus 160 equals 220 instead of the correct 260. The abstract reasoning pathway was fine, but the specific low curvature component needed for that final bit of precise addition seemed to be disrupted.
It perfectly separates the high-level planning from the low-level, brittle execution of the calculation.
Exactly. Structure versus precision, in a way.
All right, this has been a really insightful exploration. We've basically unpacked how this idea of lost curvature gives us a powerful new lens. It's not just abstract math. It maps directly onto how these models store different kinds of information.
Yeah, the core takeaway. High curvature seems to represent the shared, robust, general structure, the foundation for reasoning. Low curvature represents the accumulated mass of specialized, often idiosyncratic structures, the home of verbatim recall, but also, surprisingly, skills like precise arithmetic and recalling rare facts.
And understanding this structure gives us this KFAC truncation method, a parameter-free, unsupervised way to effectively remove memorization, potentially even better than supervised methods, especially for unseen memorized content. Plus, it can sometimes even act like a regularizer and improve generalization.
It really reframes how we might think about building and refining these models. It's about sculpting the right kind of internal structure.
Absolutely. So let's leave our listeners with a final thought to chew on, building on all this.
Okay, so the paper strongly suggests that skills like arithmetic and closed-book fact retrieval depend heavily on these brittle, low-curvature structures that seem distinct from the high-curvature reasoning core. If these capabilities live in such fragile, easily disrupted parts of the model, what does that imply about the minimum size or capacity a model might need if it were only specialized for robust reasoning tasks? Could we perhaps design training methods, maybe using curvature regularization directly to actively discourage reliance on these low curvature pathways from the start, aiming for models that are inherently more robust and less reliant on brittle memorization for essential skills?